Alright, so here we've got a real world situation. A scuba diver goes underwater. The weight of the water puts pressure on the diver, and the table shows how the water pressure on the diver increases as the diver's depth increases. So what is the rate of change of this linear function? So it's already telling you that it is linear. So I don't have to answer whether it's linear or nonlinear. I know that there's a rate of change. Because if it's linear, there's a rate of change. So what does this rate of change also represent? So I've got to find the rate of change and decide what it represents. So I'm just going to pick 2 points. So I'm just going to pick these 2 middle points. It really doesn't matter, just as long as you have 2 points. And I'm going, as you know, I prefer to do y minus y over x minus x. So 13.2 minus 8.8 over 30 minus 20. So 13.2 minus 8.8 gives us 4.4. And 30 minus 20 is 10. And so what does this rate of change represent? And so for every 10, right? Yeah, 10 feet in depth, the water pressure increases by 4.4 pounds per square inch. Or we could switch that around and say that we increase by 4.4 pounds per square inch for every 10 feet in depth that we dive. Same thing, either way that we write it. So that's part A. Part B, use the rate of change to predict the water pressure on a diver at the depth of 60 feet and a depth of 100 feet. So right now we're at 40. So if I continue this table, I'll continue it down here. 50, and then we would have 17.6 plus 4.4, so we'd end up with 22. And then 60 is 26.4. And so I can go ahead and answer that over here. 60 feet is 26.4 pounds per inch squared. And then 70, and then 26.4 plus 4.4 would bring us to 30.8. But I'm wanting 100. So 70, 80 would bring us to 35.2, because I added another 4.4. 90, if I add another 4.4, brings us to 39.6. And 100 would be, so 39.6 plus 4 would be 44. So 100 feet is 44 pounds per square inch. And so that's, I just used what I knew, that each time I was adding 4.4 and I extended the table. As long as, like, if this was 0, 0 as our starting point, I can just take the number and take it times, or I can take my x value, this is x and this is y, take my x value times our slope and I would get my y value. I just have to be careful. So a lot of times I just prefer to continue the table just in case our starting point was not 0, 0. All right, next example, last example. Suppose there are 20 rabbits on an island and that the rabbit population can triple every 6 months. So we're going to make a table of our values to find how many rabbits there would be in 2 years. So I'm telling you, it's going to be a long one. We're going to take up pretty much this whole slide, and because we're going to continue on. So you probably don't want to write very big. All right, so starting off, there are 20 rabbits on an island. So 0 months, 20, and so this is months, just so that we realize, and this is rabbits. So 0 months, we have 20 rabbits. Every 6 months, we triple. So we're going to do 6 months, and then we're going to take 3 times 20, because that's what triple means, and we get 60. And right now we're going for 2 years. So this is half a year. 12 months is a full year, and I'm going to triple the 60, which would be 180. And then another another 6 months, and we're at 18 months. And then 180 times 3 is 540. And then 18, so we're going to do 24. And then 540 times 3 is 1,620. And so this was 1 year. So this is 2 years. And so it says how many rabbits will there be after 2 years. And the answer is 1,620 rabbits. And then it says, does this relationship represent a non-linear function? Explain. Now, yes, because from 20 to 60 is 40, but from 60 to 180 is 18 minus 6, which is 12, so 120. Seems like a lot, but that's what it is. And so that's our differences. It's not a constant rate of change. And so, yes, it's nonlinear. No constant rate of change. And you may be saying, but Mrs. Cartwright, we're taking it times 3 each time. Yes, I'm taking my answer prior times 3, which is making us grow faster. And really what this would be an exponential function instead of a linear type of function. All right, so now using the table, when would we expect the rabbit population to reach 1 million rabbits? All right, so we're going to keep going. At 30 months, when I take this times 3, and yes, I've already done all this math, we get 4,860. We add another 6 months, so 36. So we're at 3 years. We get 14,580 rabbits. At another 6, we're at 42 months, and that is 43,740. Add another 6 months, we're at 48 months, in which we've made it to 131,220. And then add another 6 months, we're now at 54 months. And that is 393,660. And then we get to add another 6 months. We're at 5 years, just so that we kind of know where we are in the process. And that's 1,180,980. And so approximately 5 years before we hit the 1 million rabbits. It's a lot of rabbits. A lot of rabbits. So just keep in mind, tables can be our friends. Tables are found by using patterns. Patterns are stuff that you've been working on since kindergarten. So you know how to do patterns. We're going to keep using those patterns to continue a table once we have a table started. Until next time, 8th graders, it's been fun.